2, 1. So welcome in. Just a few examples here with regards to power. Okay, so when you are going back and forth and starting off your electricity chapter. So it's got a little bit of a review. So here's the first question. Find the amount of power needed to charge a medical device of 4.8 kilojoules in 5 minutes. Provide the answer in SI standard, so the metric standard units rounded to 2 significant figures. All right, so let's take a look here. So what do we have given? We have a couple of pieces of information here. So we have 1, which is the energy needed, and then we have how long we want this to happen over, so which is 5 minutes. Now recall that power, as you're looking through power, then power is nothing else but the change in energy, or the total work which is needed, okay, over the change in time. Well, we have both of these in here. Now they say provide the answer in SI standard units, okay, rounded to 2 significant figures. So this right here is going to be our change in energy, or the work that we need to do. And this right here is obviously going to be the time that we have. So now if we want metric standard units, well, the kilo we can change back. So that is going to be 4,800 joules. So changing it back to joules right there. And then the 5 minutes, well, 5 minutes times 60 seconds is going to give us the total number of seconds, which is going to be 300. Now, once we have that, we can calculate exactly what the power is. So this isn't a very difficult question within here. So it's going to be 300, and this is 16. Well, this is already 2 significant figures right there, so there's no rounding as well. So this is it. That's the only thing that we would need to do for this particular example. Here's the second example. So find the amount of energy. Now it says in kilowatt hours and in joules. So this is a good example because it brings you back into kilowatt hours because you're going to be working with that unit whenever you're talking about powers and electricity. Now we want to find out the amount of energy to operate 250 watts, okay, or a 250 watt device for 150 minutes, round to 2 significant figures. So we have really 2 things in here, right? Because we want to be able to do it in kilowatt hours and in joules. So first of all, if we want to know what the total energy is, so in here, so power is equal to the change in energy, or the amount of work done over time, which implies to us that the energy is needed is power simply multiplied by the change in time. So that's what we're going to be using for this. Now you can do it simultaneously. There's multiple ways of doing this, since they're asking us to do this both in kilowatt hours and in joules, so you can do the unit conversions as necessary right there. And so I'll do, left hand side, I'll do kilowatt hours, because it's actually not that difficult in order to do that straight from the equation itself. And then we can also calculate the amount of energy if we want to do it in joules. So I just want to show you both of them on the simultaneous side. So first off, in kilowatt hours. So kilowatt hours, let's do that. Well, if we want to be able to do that, let's change the power to kilowatts. So power, which is 250 watts, if you want to change it to kilo, so it's just a prefix. So this is going to be 0.25 kilowatts. That's what that equals. And then the time, and just simply change it to hours, right? So 150 minutes. So in this case, so this is going to be multiplied by, 150 minutes divided by 60 minutes per hour. It's going to give you exactly what you want. So 0.25 multiplied by 150 divided by 60. So that's not going to be too big in here. So 0.625 kilowatt hours. I'll come back to the rounding in just a moment. Now, if you want to try to get the energy, of course, as I said, you can just change this directly to joules if you wanted to. Now, kilowatt hours in joules, so there is 3.6 million or megajoules in 1 kilowatt hour. I'll put up a link up above there if you forget that conversion. between those. Or you can just go straight from the beginning. So for example, what you can do is instead here, so you know that this is again, so power times time. Well, power, you can leave in watts, so you can leave it in metric standard units. So that's going to be 250. Now remember, watts is just joules per second. And then you can just change the minutes into seconds. So that would have been 150 minutes. And 150 minutes changed to seconds is just times 60 seconds, right? So because there's 60 seconds per each minute, so the minutes will cancel. So this is going to be times 60. And therefore this is going to be seconds. So that will get rid of the seconds. And you'll have exactly what you want, which is going to be 250 multiplied by 150 multiplied by 60. So it's going to be quite a bit here. So 2250000 joules. Okay, so now I will round this. So if we want to round this to two significant figures, it's going to be 23 and then 0000 joules. Now, if you want to round this right here, well, that's going to be 0.63 kilowatt hours to two significant figures. Now, I also want to just show you, if you took this and you did the conversion directly, which you definitely could have done, so this is going to be this, and as I said, so there's 3.6 megajoules, right? So 3,600,000 joules for every kilowatt hour. So we can multiply this whole thing by 3600,123, and you're going to get exactly the same thing, right? So this is what you've got here. All right, so that's a nice exercise both from the viewpoint of converting back kilowatt hours to joules and then just understanding how you can compute the total energy. Here's the last example. So here it says a nuclear plant is 45% efficient and produces 2,500 megawatts. So it's quite a lot of power. Now, what is the amount of energy needed in 1 hour to keep the power production? Round to three significant figures. So this actually goes back to first understanding efficiency. I will put up a link up above there because efficiency typically would be introduced with the energy unit in general, and you can take a peek at that video if necessary. But recall that if you want to talk about efficiency, that was just simply equal to, in this case it was the energy that would be inputted in, so the energy that you need, and then the energy that is actually coming out. So this is the useful energy that is coming out, and this is the energy in order to make that useful energy, and that gives you your efficiency, and you would multiply this by 100%. That's what you would have there. So now, well, we're talking about power here, right? Because they give us that the total power by this, okay, this is in megawatts. We know that the efficiency in here is 45% or 0.45. If you want to change it to decimal, so that's what we have there. The time that we are talking about is 1 hour in here. So that's what we want to be able to do. So what is the amount of energy needed in 1 hour to keep the power production? Round to three significant figures. Now, it doesn't tell us to keep it in SI units or not. I guess we'll, since it's energy, we'll keep it in joules, but we'll probably kind of utilize, joules with a prefix just so that we don't have to write all the zeros. So let's take a look how exactly we would do this. So we have the total power and we have the time. So therefore, we can certainly obtain the energy. Now, if the nuclear plant is producing 2,500 megawatts, so you might ask, okay, well, which one is it? Is it this one, okay, or is it this one? Is it the energy that you would need, okay, or is this the energy which is the useful energy? Well, the production is, so the assumption here is that this is the actual useful energy. So this would have been right here. Now, of course, this is in energy terms and this is in power. Now, power is just the total energy divided by time. So you can certainly change this whole thing if you wanted to obtain exactly, okay, the same equation in power. You can just change E out to P out, so power out, and then divided by the power in, because the times, okay, that you have, you can certainly divide by the total time on both numerator and denominator. Now, they provide us in here, so notice we have the total time and the total power. So technically, we can just change this all the way through, and we can say, all right, well, what is the energy out? It is equal to the power multiplied by the time, in this case for the 1 hour. So this is going to be 2500 megawatts multiplied by. Now, if I would keep this in hours, which I certainly can, okay, so I can keep it in this way. So what I'm going to get this in, this is going to be in megawatt hours now. So this is megawatt hours in terms of the actual full out. So I'll just leave it in this case. And of course, this is just times 1. So this is going to be 2500 megawatt hours. So if you recall kilowatt hours, okay, so kilo is just 1,000, mega just means a million, right? So this is quite a bit of energy in here that we would have. So now what would I do this with? Well, the efficiency is 45%. So now I'm going to change it back in so that I can get rid of this 100%. So divide both sides by 100, so it's going to be 0.45. The energy out, so in this case, is going to be 2500 megawatt hours. And then this is the energy that we would actually need. So if it's a nuclear reactor, we would need that energy, right, from the nuclear reactions that are taking place in there. So that's what we want to be able to see. All right, so the amount of energy needed. Now, rearranging this equation, so multiplying both sides by this, so that's going to be 2500 megawatt hours divided by 0.45. This is not very difficult in here, so 2500 divided by 0.45, which is going to be quite a bit of energy. So this is 5, and I guess it's a bunch of 5s. All right, so I'll just keep it in this way. And this is going to be megawatt hours. All right, so this is what we have right there. Now, if you want to change this, so as you know, as I said, so within here, so if you want to change this now back to, let's say, joules, well, then in that case, you're going to have to do quite a bit of work here. In terms of the conversion. So notice now you're going to have to do megawatts. So now megawatts. So mega is a million. So that's going to be this. Now let's do that just for fun to kick it, okay, at the end. So this is going to be 5, 5, 5, 5.5, etc. All of these 5s. Okay, mega is 1. Okay, so 10 to the 6. Okay, right there. So that would have been mega, right? So kilo is 10 to the 3, right? Or 1,000. So this is a million. And then hours in terms of seconds, you would have to change it back. So there's 3,600 seconds in an hour. So you're going to have to do this. So notice that right here, this is going to be a monstrous number. Now, let's do it. And then we'll just put it in scientific notation. And we're going to get exactly, you know, how many joules this would be. All right, those seconds, by the way, right here would have canceled with, because watts is joules per second, right? Okay, so that second would cancel this second. So this is my answer multiplied by 3600 and then multiplied by, you know, a million. Or you can put 10 to the 6. Okay, and there you have it. So that's going to be 2 times 10 to the 13 joules. Okay, which is quite a lot, as you can see. Now, they said 3 significant figures, so I'm going to add those zeros in there so that you have it. If you've forgotten about sig figs, all right, I'll put the link, okay, up above there. All right, so there you have it. So that would have been your answer. If you wanted to keep it in megawatt hours, you can keep it in this way, round it to 3 sig figs, which would have been just 5560 megawatt hours. But if you want it in joules, okay, this is a nice exercise to test your prefix and understanding between going watt hours to joules. Okay, that is it. So those are the examples for you. So I hope that this gives you a nice introduction into calculating both powers and energies in electrical systems. Thanks for watching. See you in a future video. Bye, everybody.